Hi there, welcome to lecture 11 of Machine Learning from Data, Overfitting. Now that's a buzzword, but it's not just a buzzword. It's what differentiates the professional from the amateur. So if you can get a grip on overfitting, that's going to raise you to the level of a professional. Now, last lecture I left you with this interesting situation where on the left I'm showing you a data set that's almost linearly separable. So linearly separable modulo a few outliers. And on the right I'm showing you what happens when you throw the fourth order polynomial transform at this data. Gets in-sample error 0, but you look at this and say, really? It looks like nonsense. There's no way that the out-of-sample error is anywhere close to 0. I mean, it just looks contorted and unreal. Okay? And that actually is the typical case of overfitting, where you take this complicated, learning model, this fourth-order polynomial transform, and you throw it at a small data set that has a little bit of noise, and then you get nonsense. Okay? That's what we're going to study today. Now, before we get going, let's do our usual thing and recap where we were from last time. Last time we discussed the mechanics of the nonlinear transform. Now, at a high level, the nonlinear transform allows us to leverage all the power, the convenience, the algorithms from the linear model, but still get a nonlinear classification boundary in our original X space. And here's how it works. Okay, you start with your data that's clearly not separable by a line. Okay, and what you do is you construct a feature transform, a nonlinear feature transform that transforms this data to a new space. This new space, the feature transform space, we call the Z space. Okay? And lo and behold, in this Z space, the data is separable by a line. So you can go ahead and run your PLA or pocket algorithm or regression for classification, whatever your favorite linear model algorithm is, and find a linear classifier. Now, the thing is that this linear classifier only lives in your feature transform space. And so when you get a new test point in your original space, what you do, you transform the point using the same phi. You transform that point into your Z space, into your feature space, okay? And see, when that point is transformed into your feature space, it'll be either in the red region or the blue region, and you classify accordingly. Now, if you play this game with all possible, test points, some of them will be classified blue, and some of them will be classified red, and that, creates a separation boundary, the classification boundary, which in this case is something like an ellipse. Okay, so let's see what we have achieved. We have managed to get a nonlinear classification boundary in our original space, but we only had to deploy the linear model, albeit in a perhaps more complicated feature transform space. Okay. So the feature transform space, by the way, is under the hood. Okay, so your client comes to you with your original data, you transform, you separate with a line, and then you're ready to go for your client. And when your client looks at what you're doing, it looks like you're doing something very sophisticated and nonlinear. Little does your client know that under the hood is just a linear model, but with this powerful feature transform added on top. Okay. And since it's so powerful, it's now given you the ability to use linear models and get nonlinear classification boundaries. That's an amazing amount of power. You have to use it very carefully. Be careful. Lastly, I'll show you the digits data one more time, to which we applied the linear model, and we got an out-of-sample error approximately 2.4%. Importantly, in-sample is close to out-of-sample because it's the linear model. The linear model is good. Okay, use the linear model. Okay, and that's just with these two features of symmetry and intensity. Something like 97.6% accuracy. Pretty high, right, with just the linear model. Now we come and add the third-order polynomial transform, and because we have enough data, you can still control E in to E out. Okay, even though we've gone to a much higher dimension, you get a nice separator that looks, more reasonable perhaps. Okay, and we've managed to drop the out-of-sample error, which is still close to the in-sample error. We've managed to drop it down to 1.87. So we went from 97.6% accuracy to 98.1% accuracy or something like that. We've improved the accuracy by approximately 0.5%. Wow, all that work for 0.5%. And you might be thinking, I'm a machine learning expert and I've come with my powerful nonlinear feature transform and I've got just 0.5%. Yes, don't laugh at that 0.5%. Okay. Sometimes that 0.5%, that little bit of extra improvement that the expert, the professional brings along, that little bit of improvement is what's the difference between getting none of the business and getting all the business. So let me give you an example. Think about Google back in the day, 2025, also years ago. In those days, there was InfoSeek, Excite, Yahoo, and what are these things? You probably don't know. Maybe you know what Yahoo is, but InfoSeek, Excite, does anybody know these things anymore? They were all search engines. Okay, they were having they were all competing with each other, competing for search engine business in some sense. And then Google came along. Google wasn't spectacularly better. Now, of course, it's much better than it was, but it wasn't spectacularly better then, but it was a little bit better. And that's the way humans are. When something comes along that's a little bit better, you don't, split your business. You just go all out for the better guy, even though it's just a little bit better. We don't go to Google 80% of the time, and then when we want to search something like monkey pajamas, maybe we go to Yahoo. No, we don't. We go always to Google, no matter what it is. And so, a little bit of improvement is the difference between none of the business and all of the business, and that's a very lucrative business. So don't laugh at this 0.5%. That 0.5% that the expert adds is sometimes the whole deal. Okay, now let's talk about overfitting. Okay, so let's start our discussion of overfitting with the human ability to overfit. Now, we're all familiar with superstitions. Take Friday the 13th. Okay. Maybe historically there have been some bad events that occurred on Friday the 13th. For example, King Philip IV arrested all the Templars on a Friday the 13th, and then they were subsequently executed. So some atrocious things happened on Friday the 13th. Okay. Now, humans are very good at at latching onto these atrocious things. They make a big impression in our mind, and we don't view these as coincidences. We're looking for an explanation. And then when we find an explanation, Friday the 13th are dangerous. Okay, we're happy. We look no further. Okay, we've solved the problem. Okay, we've overfit the data. Are Friday the 13th in the future really going to be more dangerous? I doubt it. In fact, I'm willing to say that perhaps they'll be safer because everyone's so involved in this Friday the 13th fear that they're more careful. And there's even a Greek word for the Friday the 13th fear. Paraskevedekatriaphobia. I don't know if I said it right. But once you give something a word, man, it's got to be real, right? Maybe it's overfitting. Let's talk about OCD. Now we're switching gears to the medical side. And I got this citation from a medical journal, which I've since lost. So if anyone can help me find the citation, I'd be very grateful. Okay, but let me quote. The subject performs an action which leads to a good outcome and thereby generalizes it to cause and effect. The action will always give good results. Having overfit the data, the subject compulsively engages in the activity. And they use the language, having overfit the data. So it's conjectured that OCD may be a phenomenon that arises due to the human's ability to overfit, the human neural network ability to overfit. Now, let me interpret this for you in an example. For example, you want to go outside, and one day you accidentally turn the knob 3 times, the handle, okay, and you open the door, you go out, it's a beautiful day, 70s, you have a great walk. Next day, you forget, you don't accidentally turn the knob 3 times, you go out, you slip on a puddle, you injure your back. Oh my goodness. Now you're in bed thinking, wow, what did I do to deserve this? And then you think, what? Remember yesterday, I turned the knob 3 times, everything was great. And then today, I forgot, I didn't turn the knob 3 times. It must be the turning of the knob. So the next day you go out, make sure you turn the knob 3 times, because obviously you don't want to fall and injure your back. Lo and behold, it's a great day, you have a great walk. Now you've reinforced this overfit hypothesis. And you'll continue turning the knob 3 times a day, further reinforcing that whenever you turn the knob 3 times a day, good things happen. And so now you have become obsessive and compulsive with this. And it's all because you overfit the data. So humans are overfitting machines. We are very good at finding coincidences. And then looking for rational explanations. Okay. Now let's try to pin this down for machines. Okay. And I'm going to show you the typical scenario in which overfitting occurs. So here's a blue target function. It's a quadratic. Okay, I created 5 data points, and what's interesting about these data points is I've added a little bit of measurement error, so the data points are not quite on the blue target function. And since there are 5 points, a 4th order polynomial has 5 parameters, so let's try to fit with a 4th order polynomial, and you get nonsense. It's not even the case that, sure, the fourth order polynomial fits my 5 data points exactly, but it doesn't even get the right behavior as x goes to plus or minus infinity. It's going in the opposite direction as the true, blue target function. So we are nowhere close to f. We have not learned at all. And this is the classic example of overfitting. E in is 0, E out is huge, okay? And, it's because you've thrown a very complex model at a very simple, 5 example data set. But let's pause a little, think about it a little more. Let us, play the thought experiment. What if the noise was 0? So what if I didn't add little measurement error? So now the 5 data points are on the blue curve, okay? And there's a result from mathematics algebra, which says that 5 non-degenerate points can be fit uniquely by a 4th order polynomial, because you have 5 coefficients to set, you have 5 data points, and you get 5 equations and 5 unknowns you can uniquely solve. Okay, so there's a unique 4th order polynomial for any 5 non-degenerate points. If the 5 points lie on this blue target function, then the quadratic target function itself, fits all 5 data points. It is a 4th order polynomial, albeit with some of the coefficients 0, but that's fine. Okay? So then that means that this target function must be the unique 4th order polynomial that will fit any 5 data points that come from the target function. What that means is that when you fit a 4th order polynomial to the data, it will reproduce the target function, and you will have learned perfectly. Okay? So it's not just that the 4th order polynomial is too complex. The noise, the little bit of measurement error, that was very devious of me. That has made all the difference. That is what, created this red nonsense. Okay? So it's actually the coupling of the noise with the excessively, complex 4th order polynomial that ends up creating this disaster, and we need to pin it down. Let's first define overfitting. Okay? In a sentence, overfitting is fitting the data more than is warranted. I've highlighted the words more and warranted, and so let's see why I've highlighted the words more and warranted. Okay. And I'm going to show you a picture that we've seen many times. On the x-axis is the VC dimension, and the in-sample error, as you give me more and more complex hypothesis set, the in-sample error is dropping because I have more flexibility to fit the data. Okay. And, the VC analysis tells us that there's this link from in-sample error to out-of-sample error, and that's what we observe as this gap between the out-of-sample error and the in-sample error. And you observe that this gap is increasing, which means that there's bad generalization. The in-sample error is not, the link to the out-of-sample error is getting worse and worse. Okay? And that's what the VC analysis gives us. Okay, the VC analysis can be loose, and so this bound can be loose, but that's more or less what the out-of-sample error is doing. Why is this gap, why is this bound increasing? And we are now very familiar with it because the error bar depends on the VC dimension and increases as you increase the VC dimension. Okay? But that's just bad generalization. And why do I say that that's just bad generalization? It's because, what's happening here? As you give me a larger and larger VC dimension, I'm getting the in-sample error lower and lower, i.e. I'm fitting the data more and more. And as I fit the data more and more, I'm getting lower and lower out-of-sample error. And that's great, because that's all I care about is the out-of-sample error. So it's not a bad idea to fit the data more and more. So what's this business about fitting the data more than is warranted? And we get that when we continue to increase the VC dimension. So now we continue to increase the VC dimension. We continue to fit the data more and more, getting lower and lower in-sample error. But now the out-of-sample error goes up. So now, as we fit the data more and more, okay, we are getting a worse and worse final hypothesis. So fitting the data more and more in this regime is not warranted. It's a bad thing. That is overfitting. So this region where you go for lower and lower in-sample error and it results in higher and higher out-of-sample error is the overfitting region. Okay? So we like fitting as long as it doesn't produce a higher out-of-sample error. And once fitting the data starts producing a higher out-of-sample error, we say that we're starting to overfit. Now, being able to handle, understand, and sort of fight overfitting is what separates the professional from the amateur. So it's worth spending an entire lecture trying to pin down exactly what's going on when overfitting is happening. And so we're going to move to the board. Okay, so let's try to understand overfitting a little more carefully. And we'll use a very concrete, easy to visualize, one-dimensional regression setting. Okay. Now, I'm showing 2 learning scenarios on the right there. We've got a simple, 10th order polynomial target function. So that's in blue in the left picture. And you will observe that none of the data points are on the blue target function. Okay. So what that means is there's a little bit of measurement noise, measurement error. And on the right, we have a complex 50th order target function, and we've generated data, but this time the data is right on the blue target function, so there's no measurement error, there's no noise. Okay. So 2 learning scenarios. Okay. We have a simple 10th order target function with noise, and we have a complex 50th order target function f with no noise. Okay, so we have 2 learning scenarios. Now, whenever you come up to a learning scenario, you have to pick a hypothesis set. So I'm going to give you a choice of 2 hypothesis sets. So second order
polynomial fit. Okay, let's call this H2 for second order polynomial fit, and H10, which is the 10th order polynomial fit. I'll just mention, you might wonder, well, how do I do these polynomial fits? Well, the polynomial fit in regression is just the linear model, okay, with a particular nonlinear transform. So this is just the linear model with the transform that goes from the original augmented input 1x to the quadratic transform, the quadratic transformed x, which is 1x x squared. Okay, and in the 10th order polynomial fit, we go from 1x to use the nonlinear 10th order transform. Okay, and this is goes to 1x x squared, x cubed, and so on up to x to the 10. Okay, so the 10th order polynomial fit is just, and in general, the qth order polynomial fit just corresponds to a nonlinear polynomial transform. Okay, so you have to pick now. You have to pick either the second order fit or the 10th order polynomial fit. So you have to pick H2 or H10. Okay, and now when we run this class live, I will, ask you guys to decide for each machine learning scenario, you pick the second order fit or the 10th order fit. Okay, so for the simple F with noise, you pick the second order fit or the 10th order fit. For the complex, F with no noise, you pick the second order fit or the 10th order fit. Okay, so, pause the video. 1, 2, 3 seconds. Okay, now if you're coming back, okay, write down, I hope you've written down what your pick is. And now I'm going to go through, plausible justification for the various choices. Okay, so let's start with a simple 10th order target function. Okay, so this is a 10th order target function. I'm telling you that it's a 10th order target function. So it's a no-brainer, right? This is here we have an opportunity to fit the 10th order target function with the 10th order hypothesis. So it seems like, the 10th order polynomial fit should have a good chance of extracting the 10th order target function. So maybe we should choose this guy. Okay. But we saw earlier that, when you add a little bit of noise, it can throw things awry. So the only thing that might perhaps make us go for the second order polynomial fit is that there's a little bit of noise in the data. So noise might, tell us that we might want to, not go for the 10th order complex model. You can think of this as the complex learner. This is the simple learner. Okay, there's the complex learner, and then there's the simple learner. Okay. It's interesting to also think about the second learning scenario on the right, where you have a complex target function, but there's no noise. Okay. Now, here we see that both of our polynomial fits are deficient. There's no way to fit a 50th order, target function with either a 10th order or a second order. Okay. But now we see that, well, there's no noise in the data. There's no measurement error. Okay. And so, the second order fit is going to have no hope whatsoever. Okay. So, no hope. Okay. And the 10th order fit, while it's still a bit deficient, at least has some chance of getting all the variability of this blue target function. Okay, so we think that, this is a no-brainer here. Okay, so in this case, the 10th order fit is a no-brainer because look, you told me the target function is 10th order. So obviously, I should use the 10th order fit. And then here, the 10th order fit is a no-brainer because obviously, there's no noise in the data, so the data is clean, so it's going to give me all the information I need. And why would I go for this second order fit, which has no hope of fitting the 50th order function? Why would I go for that guy instead of the 10th order fit? Okay, so let's see the results. Now, in this particular example, I can synthetically generate the data, I can synthetically repeat the experiment many times, and I can show you what happens. Okay, and there's a sample of what happens. Okay, so when you fit the simple target function with noise, okay, you can either use the second order fit or the 10th order fit. The second order fit is in green, and the 10th order fit is in red because it does very badly. Okay, so this guy, does badly, pretty high error, and you can see the numbers on the right. Okay, and the 10th order fit in this scenario is a total and utter disaster. Okay. But in this case, it's pretty bad. And the interesting thing is my plausible reasoning, that suggested that H2 was probably not the right guy to go for, okay, wins in both cases. Okay. So this was wrong. It's wrong. Okay. So now, let's try to pin it down. And, I said, well, this is a course, and, there's a famous saying that if you're giving a presentation, and your presentation has 20 slides, it's usually the case that, only one of those slides, or at most, as the saying goes, at most, one of the slides in your presentation is where all the money is made, is worth listening to. And if you're lucky, it's exactly one slide. And you should sort of, highlight that one slide and say, this is the slide where you need to pay attention. Everything else is sort of peripheral. Now, this is a course with 27 or so lectures. And in the same spirit, a few of these lectures are where we're going to really get our money's worth. Okay? And this is one of those lectures. And pay attention. Okay? Because, let me be a little bit careful and slow in what we are saying here. And this is not, my opinion. Okay? We see the data on the right. Okay? So what are we saying here? What we're saying is that, so let's have a conversation between me and my boss, or you and your boss. So your boss comes to you and says, John, I'd like you to learn this target function f. It's a 10th order polynomial representing this, that, and the other. It's a 10th order polynomial. And, you ask your boss, how do you know it's a 10th order polynomial? Well, it's a 10th order polynomial, I'm telling you. We've done the theoretical physics and we know it's a 10th order polynomial. We just don't know the coefficients. Oh, okay, good. Okay, well, do you have data? These are the standard questions that you ask as a machine learner. Yes, I have data. Is it accurately measured? No. There's some measurement error. Oh, okay. So, you come to your boss. And what do you tell your boss? You tell your boss, you know what? I'm going to fit your data with a second order polynomial. And your boss is going to look at you and say, what? What? Are you crazy? I told you it's a 10th order polynomial. And you say, well, I'm choosing to fit with the second order polynomial. And your next door neighbor, okay, says, yeah, you told me it's a 10th order polynomial, so I'm going to fit with the 10th order polynomial. So obviously, you get fired. And then your boss goes and gets the 10th order polynomial fit, that red guy on the left, and uses it in practice and gets absolutely slammed. And now thinks, wow, that guy I fired, that guy was going to use the second order fit. Maybe there's something to that. So now, fire the guy who used the 10th order fit, okay, and come back to you, but now you'll ask for twice the salary. And it's because you were able to say something that was so utterly counterintuitive, but it was correct. And that's why this is where the money is, the ability to handle overfitting. What's going on here is that even though you know that the target function is 10th order, it is possible for the 10th order fit to overfit. The 10th order polynomial fit can overfit, even though you know the target function is 10th order. So you are better off ignoring that knowledge about the target function being 10th order and going with the simpler second order fit. That's what you're telling your boss. Thank you very much. You told me it's 10th order. I'm going to use second order. And if the boss asks you why, it's because you told me there's measurement error, and I'm afraid the 10th order fit might overfit. The 10th order polynomial might overfit. And even though that's the right order, it's too dangerous to use it to learn. That's where the money is. Very counterintuitive. Now, we saw earlier that if there was no noise in the data, okay, the 5th order polynomial would get exactly the target function. Okay, so you're reasoning along the same lines, okay, with your boss, let's say, in the room. You know what? If it was a 10th order target function with no noise, I would certainly use the 10th order fit. Boss says, yeah, that makes sense. There's no noise. The 10th order fit will exactly capture, it's uniquely determined as long as I have at least 11 data points. It's uniquely captured by the, 11 data points. I can uniquely pin down a 10th order polynomial. And so if there's no noise, you'll get me the target function. Yes. Okay, good. So you and your boss agree that if the target function you were trying to fit was 10th order with no noise, you'd go with the 10th order fit. And then the boss says, wait a minute, I just called up engineering. And engineering just told me they found a bug in their derivation. The target function is not a 10th order polynomial. It's a 50th order polynomial. But still, yes, they can get perfectly accurate measurements. So it's now a 50th order polynomial with no noise. So you look at the boss and you say, that's interesting. Well, in that case, now that the target function has gotten more complex, the target function has gotten more complex. I'm going with the simpler model, the simpler second order polynomial. And the boss looks at you and says, are you smoking something? What? We agreed that if the target function is 10th order with no noise, you'd go with the 10th order fit. Now I'm telling you the target function is 50th order, and you're going with the second order fit. I say, yes, because we only have 14, we only have 13, 14 data points, so I'm going with the second order fit, even though we agreed that with 10th order target function, I would go with the 10th order fit. And the boss is looking at you. And let's see, why is what you're saying so counterintuitive? The target function has got more complicated. And it's better to go with the less complicated hypothesis. What? Okay, at this point, you should be saying to yourself, what? You should be reeling backwards, falling over. I mean, it's completely counterintuitive. And all of this has to do with overfitting. Okay. So basically what's going on here is that even though the target function got more complex, you are now getting less complex as the learner. Very counterintuitive. So your boss tells you the target function order, you don't use the order of the target function even though it's available to you. Your boss tells you the target function is getting more complex, you are becoming less complex as a learner. And that turns out to be better. Depends, of course, on the number of data points. And that's what we're going to investigate. Okay. But before we get there, I just want to show you that I kind of pulled a con on you. Okay. So I showed you, two learning scenarios. Okay. What were the two learning scenarios? Simple F with no noise and, complex F with, simple F with noise and complex F with no noise. Okay. And repeating those two scenarios there. And then you had to make a choice between a simple hypothesis set and a complex hypothesis set. Okay, so what's the con? There's no con. The con is that I deliberately showed you the target function, okay, which then I identified for you that, on the left there's measurement error and on the right there's no measurement error. Okay, and showing you the target function was the con. You say, what? How can it be a con? That can only help me. No, because, in practice, you don't get to see the target function. You don't get to see the target function. You only get to see the data. Now, by showing you the target function, you were able to identify, there's measurement noise on the left and it's perfectly pure data on the right. But in practice, you can't tell the difference between the left and the right. You don't know if the left is a complex target function with no noise or a simple target function with noise. Same thing on the right. Look at the data that you would see when you approach the problem as a machine learner. That's what you would see. And you can't tell whether there's noise or not, and whether the target function is simple with noise or complex with no noise. So actually, both of these learning scenarios, when you look just at the data, are very similar learning scenarios. And as the learner, you cannot tell the difference between the two. So it's actually no surprise that in both cases, it's the same model that wins. And what matters is not that you match your hypothesis set to the target function. What matters is that you match your learning, your hypothesis set, to the data. It's the data that matters. That's important. That, it's not the target function that you should be worried about. It's the data, the quantity and the quality of the data. That's what should determine what you do. Okay? Not this sort of peripheral information about the target function. All right. So, we're going to study overfitting now. We're going to now try to pin it down a little more. Okay, now we saw this illustrative example. And so, let's define a measure of overfitting. Okay, in this context of second order and 10th order fits. Okay, and then we'll go to the slides and see some real data, some real pictures. And, stay tuned because I'm going to show you the pictures today that are in some sense a logo for this course. Okay, and the pictures that you're going to see today are from real data. And they are the pictures on the front of the book. Okay. And so, if these are the pictures that are making the front of the book, we had a reason for choosing that. Those are very important pictures. And they're going to make an appearance today. So it's a star-studded lecture. Okay, so let's talk about overfitting now. Try to now make it a little more quantitative. Okay, so we saw these very stunning conclusions. You know the target function order, yet you may choose a simpler hypothesis set. The target function got more complex, you go simpler as the learner. Wow, imagine standing up and telling this to your boss. They'll think you're crazy, and then they'll have to pay you double when they get, messed up by not following the expert who knows how to handle overfitting. Okay. So, the overfit measure and overfit measure. Okay. So we know that for H2, the second order fit, and if we compare H10, okay, so you have E in of H2, whatever in-sample error this guy can attain, is going to always be at least as large as E in of H10. Okay, so it's always the case that if you go for H10, you're going for the better fit. You're going for the lower in-sample error. Okay, so if E out of H10 is greater than E in of H10, then we have overfit, right? Because E out of H10 is greater than E out of H2, then we have overfit, right? Because we went for the lower in-sample error, okay, and got a higher out-of-sample error. So we fit the data more than warranted. Okay, so we can define an overfit measure, which quantifies how much we have overfit. We'll define an overfit measure, which is just E out of H10 minus E in of H10. Okay. And the higher this number is, the more the overfitting. The lower this number is, the less the overfitting. Okay. So now let's go to the slides, and I'm going to show you some curves where we study this number. So, some of the parameters that we can, mess around with in our sample scenarios, and we can do this, because we are generating these, they are artificially generated sample scenarios, but they're still real data, just that, we control the scenario. Okay, so we can control, what can we control? Okay, so we can control the amount of measurement error. So the noise, let's call that noise, or measurement error. And let's call that sigma squared. Okay, the variance in the measurement errors. Okay, and the larger the noise, the larger the measurement errors. Okay, we can certainly control the number of data points. Number of data points. Okay, so N. And we can control also in this scenario, because we are generating the data and the target function, we can control the complexity of the target function. We can control the complexity of f, the target function. So, and one way to quantify that is the degree of the polynomial q. Okay, so this is the degree of f, the degree of the polynomial, we can call it q. Okay. So what we're going to do is we're going to generate a variety of scenarios, learning scenarios, where we systematically vary the noise, the number of data points, and the complexity of the target function. And let's see, when does overfitting occur? Okay, so we can compute this overfit measure and see when does overfitting occur. So let's erase the board. Well, let's move to the slides. Okay. Okay, so first, let's vary on the x-axis the number of data points. Okay. And on the y-axis, we've got this noise level that I talked about. Okay, so noise increasing, number of data points increasing, and for each choice of the number of data points and the noise level, we will assume that the target complexity has remained constant. And what I'm showing in a color-coded way is the overfit measure. And red means higher, blue means lower. Okay, and it's very easy to see a pattern here. Okay, which is that as you have more and more data points, you move from the red region to the blue region. So more data results in lower overfitting. Okay. If you fix the number of data points that's at 100 and start increasing the noise, the overfit measure gradually gradually increases, and eventually flips over to positive, which means you're overfitting. So this deep red region is the region of severe overfitting, and this blue region is the region where there's no overfitting. So in the deep red region, you'd rather choose your H2, your second order fit, over the 10th order fit, and in the blue region, you would rather choose your 10th order fit over your second order fit. So let's summarize. When you have a small number of data points, okay, almost independent of the noise level, go with the simpler fit, okay, H2. When you have a large number of data points, okay, in this region, okay, as long as the noise level is small, you can go with your more complex 10th order fit. Okay, but as you increase the amount of noise, get ready to shift over to your second order fit. So more data points, overfitting down, more noise, overfitting up. And that we might say is sort of what we expected from intuition and maybe, folklore knowledge. Okay? And here I'm showing it to you in this beautifully, color-coded image. And like I said, okay, this image is one of the headline images. It's on the front, it's on the front of the book. It's a very important image, which says that get ready to switch over from the more complex model to the simpler model. When your number of data points goes down, or the amount of noise in your data goes up, and it's sort of you get the same picture no matter what the complexity of the target function. So even if the target function has 10th order polynomial complexity, you still will switch over to the second order polynomial for a small number of data points and a high enough noise. Okay. Now, let's vary the number of data points and the target complexity to see how the target complexity affects things. And we get the second picture that's, on the front cover of the book. These two pictures are very important. And you see a very similar picture in terms of where is the blue and where is the red. Now, these nice linear, color-coded regions is due to the fact of the linear model and the way noise affects the out of sample error. Here we have the target complexity, and you still have these red regions and the blue regions, similarly, positioned. Okay, and the message is still the same. Okay, that if you have more and more data points, you get into this blue region, and you can afford to pick the 10th order polynomial fit, for various degrees of complexity for the target function. But as you have fewer and fewer data points, and in this case, we've kept the noise level is fixed. As you have fewer and fewer data points, get ready to switch to the simpler second order polynomial. Okay? And that doesn't really matter whether you're dealing with a very complex target function like 100th order or 25th order. Okay? And basically, as you have, let's say you have 80 data points and a 25th order target function, you still go for the simpler fit, even though it has no hope of fitting a 25th order target function. It's deep red region, lots of overfitting. The second order polynomial fit is significantly preferred. Okay. So what's the message here? The message here is that, as the target complexity goes up, here is a very counterintuitive message. As the target complexity goes up, you should prefer the simpler model. Imagine telling that to your boss. Boss, since the target complexity is going up, I'm switching from the 10th order fit to the second order fit. What? Yes. To avoid overfitting. And this is not conjecture. This is concrete. This is quantitative. The overfit measure has gone into deep red territory, okay, as the target complexity goes up. Okay. And so, what we're going to try to do is now understand why these two pictures are so similar. Okay. And in doing so, we're going to unify the target complexity with the noise level. Okay. So let's go back to the board. Okay. So it turns out that, both of those concepts that, as the noise level in the data goes up, get ready to switch from the complex hypothesis set to the simpler hypothesis set. As the target complexity goes up, counterintuitive, get ready to switch from the more complex model to the simpler model. So as the target complexity goes up, you want to switch to the simpler model. Very counterintuitive. Okay, now, both of these sort of effects can be captured with a careful definition of what noise is. Okay, and so we're going to talk about noise. Okay, and on the right, I'm showing you the definition of noise, and I'm choosing my words very carefully here. Okay, so noise is the part of y that we cannot model. Okay, and it's very important there to sort of appreciate the highlighted words, the part of y that we cannot model. Now you might think, well, why did I put y there instead of f? Why isn't noise the part of f that we cannot model? And that'll become clear shortly. So it's very important. It's the part of y. What is y? Y is the observed, value in the data. So you have x and y. Y is observed. Now, in the noiseless case, y equals f of x. But when there's measurement error, y may not necessarily equal f of x. And so noise is the part of y that we cannot measure. And it has two sources. And that's what we're going to discuss carefully. So noise has two sources. And the first is the obvious thing that we just, are all familiar with, which is this measurement error. Okay. So we're going to call that stochastic noise. Stochastic noise. AKA measurement error. You might wonder, wow, okay, we have a fancy name for this? Yes, we call it stochastic noise. And you should be thinking, well, maybe there's some other kind of noise, and stay tuned. Okay. So let me give you an illustration of stochastic noise in a sort of mathematical, concrete setting, and then I'll show you an example from the real world. Okay. So stochastic noise. So think of, the regression setting. Okay. And, you have your target function, which I'm going to put in blue to be sort of matching with the slides. Okay. And, you're going to generate a data point. So you generate an x value. Okay. And this is f of x. So this is f of x. This is f of x. Okay. But there's measurement error. So you don't measure f of x. You measure f of x plus some noise. F of x plus some noise. Okay. And so this is noise. Okay. Epsilon. And so in this case, okay, y, the observed y value in your data is equal to f of x plus epsilon, which is the noise. And what's typical about such measurement errors? They're random. Okay, so they're random. And, you would much rather learn from, y equals f of x. You'd much rather learn from that. Okay? But you only got to observe, f of x plus epsilon. You got to observe the noisy version of f of x. And there's no way, there's nobody, there's no hypothesis set that, that anyone can work with that can model noise. Noise is in some sense the most complicated function that you could think of. Okay. So imagine I repeated this process for all the x's. I generated the target function plus noise. Here's what it would look like. Okay. So here's what it would look like. Okay. I might generate, that point, and then this point, and then this point, and then this point, and this point. So if I generated a target function with noise, okay, it might look something like this. Okay. And you see that the observed y value deviates from the blue target function by the amount of noise added. Okay. And so in some sense, this is the y value that we observe, and there's no way for us to model this very complicated, random noise is just super complicated. There's no way for us to model that black curve, but it's that black curve that appears in the data. And so the part that we might have a shot at modeling is this blue curve, but we don't get to see that. So the data, the y value contains a part that we have no way of modeling. Okay, and that's what we call the stochastic noise. Okay, so this is the stochastic noise. Okay, now what happens? What happens is that maybe in our hypothesis set, so let's now imagine we generated a data set which is, this guy, that guy, and let's say that guy, just to be concrete. Now, maybe in our hypothesis set, we might be able to model the target function relatively closely. So let's say with that red dotted curve. Okay. But when we observe these data points which are the y values which contain the noise that we cannot model, okay, we don't know that we cannot model that noise. So we use our hypothesis set, let's say the 10th order fit, to try to model that data instead of the target function. Okay, and we're going to output maybe something that looks like this. Okay, because it's fitting the data which contains something we cannot model. We are trying to model something that we cannot model, and in the process, we produce junk. Okay, nonsense. Okay, so in trying to model the thing we cannot model, that's what leads the learning astray. And that's basically what overfitting is. Overfitting is when you see there's noise in the data, you try to model it, i.e. you try to fit that part of the data that you shouldn't try to fit because you can't model it. So you're fitting the data more than is warranted because you're trying to fit what you cannot model. And then you produce something with huge out-of-sample error, something that's basically nonsense. So this is the result of the overfitting, which is led astray by the noise. Led astray by noise. Okay. And now you can see why the complexity of the hypothesis set, which is comes in, which is where people think of the traditional kinds of overfitting, is that, your ability to do this kind of, complicated fit to the data relies on the fact that your hypothesis set is complex. So it's easier to lead a complex hypothesis set astray than it is to lead a simpler hypothesis set astray. And hence, as the level of measurement noise in your data goes up, you should switch from the complex hypothesis set to the simpler, not because the simpler one has a better shot at approximating your target function, but because the simpler one has a less of a chance of being led astray by stochastic noise, which you cannot model. So by the fact that you cannot model is another way of saying it's going to lead you astray. Okay. So that's stochastic noise. Now let me show you the other source of noise. And this is the source of noise that many people will tend to ignore. And this is what leads to the very counterintuitive sort of advice that as your target function complexity is going up, go with the simpler hypothesis. I'm going to show you I'm going to show you a very similar picture to that. And you'll be stunned at the similarity. Okay. So we're going to call this deterministic noise. Deterministic noise. Okay. Now, just before we go into, deterministic noise, let me show you an example of stochastic noise and look at the elephants. Okay. So there's the clean picture of the elephant, and you can try to learn what an elephant is. And it's no surprise to you that if I showed you that very noisy picture of the elephant, it's going to be harder for you to learn what an elephant is. Because you might get hung up on, that black pixel on the top, left. Okay. And that black pixel on the top left is just noise. Okay. And if there happens to be a black pixel on the top left for 100 images, just by chance, okay, there's a black pixel on the top left where it shouldn't be because of noise. Then the machine learner will hone in on that, okay, and somehow fixate on the fact that black pixel in the top left is what makes an elephant, and it's complete nonsense. Now a human has a very good ability to sort of simplify the right picture and extract the low-level pattern of the elephant. And, it's important to ask, can we get a machine learner to do the same thing? Because when a human looks at the right picture, they say, yeah, I can see there's noise there, but, it's really underneath there's an elephant. The machine learner, if left to itself, might hone in on the top left black pixel. Okay? Because that's what the data shows. Okay. Let's talk about deterministic noise, the other source of noise. Okay. And to illustrate, remember, the noise in general is the part of the y value you cannot model. Okay. So, in order to discuss deterministic noise, let us fix the hypothesis set. Fix the hypothesis set. Now, this is a new concept. Okay, we're all familiar with measurement error. Deterministic noise, isn't that an oxymoron? Watch. Okay. So, fix the hypothesis set. And let's draw a similar picture. Okay. But now I'm going to draw for you a super duper hyper complex target function. Because remember, I'm trying to unify those two, nice colored pictures that are on the front page of our book. Okay. And on one of the pictures was showing you the dependence of the overfit measure on stochastic noise. And the other showed you the dependence of the overfit measure on the target complexity. So let's see what happens if you have a very complex target function. Okay. Now, as a target function gets more and more complex, it's usually the case, and certainly the case with a fixed hypothesis set H. Okay. And everyone tell me, why do we have a fixed hypothesis set H? It's part of the learning problem setup, right? You have to fix the hypothesis set before you look at the data. So you have a fixed hypothesis set H. Now, as you get a more and more complex target function, we can imagine, okay, that there is some best hypothesis in here that approximates the target function, not the data, the target function. Okay. So let me draw that as a red curve. Okay, so imagine that, your hypothesis set is limited, and so it may not have all this wiggliness capability. Okay, let's say it's second order polynomial or third or 10th or whatever. Remember, we did the 10th order polynomial versus the 50th order. So your fixed hypothesis set has a set of hypotheses. Let me, heuristically illustrate that with, the set of hypotheses. And one of them in here will be the best hypothesis. Okay, let's call this best hypothesis H star. Now, this has nothing to do with the data. Okay, this has nothing to do with the data. This is just, given that this is the target function, this is the best hypothesis, H star. And let me draw what that might look like. Because you've got a fixed hypothesis set and a very complex target function. This H star might look something like this. Because it's a simple hypothesis set relative to the target function. Because remember, we're looking at the target function with hypercomplexity. Okay, now let's play the same game. Let's play the same game. Okay, so you generate a data point X for your data set. Okay, so you generate the data point X. And now let's see, what is the Y value going to be? What is the Y value going to be? The Y value is going to be, in this example, is going to be this guy here. Okay, so this is f of X. And we're considering the case with no noise now, no measurement error. You might think, well, what is there measurement? No measurement error. Okay. So this is f of X. So Y equals f of X. Wow, fantastic. That's very different from here. Right? Here we added measurement error. But I'm going to point out now, okay, that, is this a good target to learn from? Okay. And I'm going to point out that we can reformulate the goal of the learning as, please produce for me H star. Why? Because H star is the best hypothesis in your hypothesis set. It is just the best. It's flat out the best. Forget about the data. It has nothing to do with the data. It is just the best hypothesis in your hypothesis set. So, you would have accomplished the best you can accomplish. So the optimal outcome for your learning is H star. So the optimal outcome for your learning is H star. You cannot do any better because that's the best. Okay. So what is the best data point for you to learn from? The best data point for you to learn from, if your goal is to output H star, the best data point to learn from is Y star is equal to H star of X. So you would much rather be given this data point. Okay? Not this data point. Right? Because, imagine that we've reduced you to a target function that is within your capability, which is H star. And to learn that target function, you would much rather see the data point X Y star equals H star of X. In other words, H star of X is what you can model. The target function is too complex for you. Okay? So if we define this as another kind of noise, ta-da, deterministic noise. So this is, you can think of this as a noise, epsilon. Okay? Then Y is equal to H star of X, what you can model, what you like to learn from, plus a perturbation, an epsilon. And this perturbation from what you would like to output is what we call the deterministic noise. Wow. Okay. And it has the same effect on learning. Now, why do I say that? Because you would like to output this red curve. But now you see a few data points that are involving y, which has a part of the data, which has a part that you cannot model. So you try to model those black data points. And if your model has sufficient flexibility, you might output, instead of this curve, this red curve, you might output this red curve, okay, which is much worse. Okay. So the little bit of the target function that is beyond your capability is leading your learning astray, just like stochastic noise. That little bit of deterministic noise, okay, is leading your learning astray. Now, why are we saying it's leading your learning astray? Because you cannot approximate f. You might as well go for the best thing that you can approximate. And that little bit of f that you cannot model is leading you away from h star. And in so doing, it actually ends up leading you away from f, because h star is the best that you can do. So, if you look at this picture and play the same game with all the possible values of x, you'll see that there's a part of f that you cannot model. Okay, and I'm shading in that part of f that you cannot model. You'd much rather see data from, this red h star of x, okay, but you don't have access to the data. Okay, and so this part of f that you cannot model, now you look at these two pictures and they're very similar. Okay, so an excess complexity in the target function f has almost the same effect as a large amount of measurement noise. In both cases, they take you away, they lead you astray from what you would like to do, from what you can do. Okay. So this deterministic noise leads the learning astray. Now, there's a fundamental difference between the deterministic noise and the deterministic noise and the stochastic noise, in that, if you regenerated the same x point and a new y value, in the stochastic noise case, you'll get different y values. The deterministic noise case, you get the same y value. So if you regenerated the same x point, you'll get the same y value. So deterministic noise, that's why we call it deterministic noise. It doesn't change with the same instance of x, but repeated generation of that data point. So hence the term deterministic noise. There's another very subtle difference between deterministic noise and stochastic noise. Stochastic noise leads to a deficiency in the hypothesis set, okay, in being able to model y, no matter what your hypothesis set, because nobody can model the noise, random noise. But with deterministic noise, there's sort of an arms race. So you can think that if your hypothesis set gets more complex, then the deterministic noise will shrink. Okay? And so it seems if you make this sort of naive analysis, that in order to lower the deterministic noise, you should make your hypothesis set more and more complex. But there's a trade-off. Okay, remember, what the noise is doing is leading your hypothesis set, leading your learning astray. And so that comes to bite you in the back when you make your hypothesis set more complex to reduce the level of deterministic noise, but the effect of the deterministic noise is more. So as your hypothesis set gets more complex, even a little bit of deterministic noise leads you far astray. So there's an arms race there, and that's a subtle trade-off, and another subtle difference between deterministic noise and stochastic noise. But as far as the learner is concerned, once you've fixed your hypothesis set and once you've generated the data, the learner cannot tell the difference between stochastic noise and deterministic noise, because in both cases, it's a part of the y value that you cannot model. And in both cases, it leads you astray just the same. And here is an example of real-world deterministic noise. You don't believe me? Look at this example. Okay? And have in the back of your mind that the ideal data point for me is x, and the simplified h star of x, as opposed to versus x and the more complex y, which is f of x. This is the ideal data point. Okay? That's the ideal data point. Okay? But we get the more complex data point, and we would learn much better if you could give me instead the simpler data point, the one that contains only the part that I can model. Okay? And so here's an example, of learning human learning. Okay, and on the left I show you that elephant again. Now we're trying to teach the 2-year-old or the 3-year-old what's an elephant. And so you scroll through the picture book of the 3-year-old and you come to the thing on the right, which is called an elephant. Everyone and their mothers knows, including grandmothers and grandfathers and fathers and cousins, everyone knows that the thing on the right is not an elephant. You'll never see the thing on the right in the real world and call it an elephant. Okay? So why does the picture book have that guy, that simplified elephant? Because we have a simple hypothesis set. A 3-year-old is trying to learn what an elephant is. And they have certain capabilities. And if you show them that complex thing, they're going to get led astray. You've got elephant, it's got lines on the trunk, there's grass, all kinds of things that are leading the simple learner astray. And they learn much better from the simplified data point, the one that is h star of x. And from the simplified data point, they capture all the essence of the elephant, okay, while ignoring the details. Okay, the big ears, the trunk, the tusks, the general heavy-weightedness, and so on and so forth. Ignoring all the minute details. To appreciate the minute details, you need to become a much more complicated machine learner, a much more complicated hypothesis set, and you need much more data so that you don't get led astray from little deviations. Okay. So, noise is what leads learning astray. Okay. It comes in 2 forms: stochastic noise, measurement error. You can't do anything about measurement error. Deterministic noise is the part of the target function you cannot model. You can try to do something about deterministic noise, but you must be careful. There's a trade-off. There's an arms race. If you try to make your hypothesis set more complex to lower the deterministic noise, your hypothesis, your learning will be more likely to be led astray by much larger amounts. Okay, so there's this arms race. Okay, now when we come back, I'm going to show you, how all of this sits within the bias-variance decomposition that we talked about. Okay, and then we'll sort of summarize. So let's erase. Switch off the slides. Okay, so we studied the bias-variance decomposition as a tool for decomposing the out-of-sample error, the expected out-of-sample error, in terms of a bias and a variance. Okay, and it's relatively straightforward to add noise into that decomposition, especially when the noise is measured by the variance of the measurement error. Okay, so let's just do that, and then let's interpret the result, and it gives us a nice way to sort of see how changing the hypothesis set or changing the learning algorithm or what have you will affect the out-of-sample error by trying to optimize the various terms in this decomposition. Okay, so the bias variance decomposition with stochastic noise. Okay, so that's what we're going to talk about. And I'll just remind you, the bias variance decomposition when there was no stochastic noise was that the expected value of E out was equal to 2 terms, which was, the bias plus the variance. Okay, and what was this term? This was, in some sense, G bar of x minus f of x squared. And this term was the variance of G of x, where, the variance and this expected value and this variance and this average function that you output are all with respect to the randomness coming from the data set generation process. Okay, so when you generate random data sets, there's some average. So this is E out of x. So there's some average value you will output, and there's some variance. Okay. And let's see what happens when now there's noise. So how did we get this? Okay, so now the E out of x was equal to G of x minus f of x. Okay. And this was in the noiseless case. In the noisy case, E out of x is going to equal G of x, okay, minus y squared. Because now, we're looking at the output y, and the output y compared to the prediction G of x, and the output y is equal to f of x plus your noise, epsilon. So this is equal to G of x minus f of x minus epsilon. So this is equal to G of x minus f of x squared plus twice epsilon g of x minus f of x plus, minus, plus epsilon squared. Okay. Now, we're interested in your expected out of sample error, so let's take the expected value on both sides. So this is E out of x. So the expected value on both sides gives me the expected value of this guy minus twice the expected value of this guy plus the expected value of this guy. Okay. Now, if your noise, your measurement error is zero mean, so it's equally likely basically to be positive or negative, so you can equally likely make mistakes, up or down. Okay. Then, and assuming that your measurement errors are independent of basically f and g and x, so the measurement error is this totally independent random measurement error, then this is the expected value of two terms that are independent, so you can separate the two terms out. This is the expected value of epsilon times the expected value of g of x minus f of x. The expected value of epsilon is now 0. Okay, so this term is 0. And so we end up with the term that we had before, averaged over data sets, which this term is exactly equal to the bias, okay, plus at x, plus the variance at x. Okay. And then the expected value of epsilon squared, if the expected value of epsilon is 0, this is just the variance of the noise, so plus sigma squared. Okay. So let me summarize. Let's summarize that your expected out of sample error, and you can view it either as a function of x, or you can take the expected value over x. Okay, so the expected out of sample error is equal to your bias plus sigma squared plus, make these pluses in black, plus okay, your variance at x. So let me write that in black. So your variance, not variance, just variance. And because we've taken the average, let's say, with respect to x. Okay, and let's interpret this. This is a very interesting breakdown. And this is an equality. So your expected out of sample error is your bias plus your measurement error variance, plus the variance in the final hypothesis, okay, that you output. You can think of this, the bias, remember it's G bar minus F. Remember when we discussed bias variance, this is what? This is, the best you can do. It's how well you can do. Okay. So how well you can do basically quantifies the deterministic noise. Okay. It's sort of the difference between the best H star in our previous discussion and F. Okay. And H star is roughly speaking G bar of X. So this can be interpreted as the deterministic noise. Well, this guy is exactly the stochastic noise. By definition, it's the variance of the measurement error. So this quantifies the stochastic noise. Okay. And this variance is the interesting guy. What is this variance? This variance is in some sense the indirect impact of these two types of noise. Okay, what is it arising from? It's arising from the fact that every time you generate a data set, you might output a different final hypothesis G. And the more noise there is, the more easily it is to be led astray and output random, wild final hypotheses. So if there's no noise, you'll pretty much always be outputting the best you can output, which is close to F. Okay. But when there's noise, okay, the variance is the indirect impact of the noise. And that's both kinds of noise. Okay. And that indirect impact can depend on your hypothesis set H and the number of data points, very importantly. The more complex your hypothesis set, the larger this indirect impact. But also, it's possible that the bias gets smaller, but you still have this guy here who's going to lead you wildly astray. And it's always the case that there's noise in data, measurement error. And this guy is going to prevent you in a significant way from going to larger and larger, more complex hypotheses. That's due to this variance indirect impact. Okay? But the sure way to lower the variance is to increase N. When you increase n, increase the number of data points, the impact of the indirect impact of the various noises gradually drops away, and then your out of sample error will basically be basically be the sum of, the deficiency of the hypothesis set measured by the bias and the measurement error. And those you cannot overcome no matter how many data points you get. Okay? This is a very nice breakdown of your expected out of sample error. And when you're designing hypothesis sets and learning algorithms and so on and so forth, you can always look at this decomposition, even though you cannot measure any of these, and ask, am I trying to lower this guy, the bias, or am I trying to lower the variance? You cannot lower the measurement error. That's just measurement error. So this is there always. And through this, you will feel the impact in the variance. Okay, always. Okay. So this guy will feel this impact. You can try to lower this, but therefore you might increase the impact of this guy by a larger, more complex hypothesis. So a lot of interesting challenges for the machine learning expert and a lot of interesting choices that the machine learning expert has to make. And this decomposition can help a lot in making those decisions. Okay. So let's erase. Okay, so let's summarize what's going on in this lecture. And, it's been a mostly conceptual lecture, not much math and derivations and this and that, but the concepts have been very important. Okay, because overfitting being able to handle overfitting is what separates the expert from the amateur. And we saw certain very counterintuitive things, like, if your target function complexity is going up, then you had better start thinking about simplifying the learner. That's very counterintuitive. Okay, you learned it here. Okay, now, just to summarize, you can think of overfitting as a disease, and the virus, what's causing the disease is noise, both kinds of noise. And we sort of gave this general definition of noise as, that part of the data which you cannot model, which the learner cannot model, and in trying to model it, you are led astray. Okay? And you can bet your bottom dollar that in any application you are going to be faced with in the future, you will have measurement errors. You will have stochastic noise. We just don't have perfect measuring instruments for pretty much any application. So noise is always there. And it's pretty much always the case that you will have deterministic noise, because the type of target functions that we're trying to learn in complex applications that have big impact tend to be complex. Okay, so there's always noise, okay, and it's leading the learning astray. And so we need to be able to deal with this. Okay, so we're going to study next, regularization, which is a technique for dealing, it's a cure for overfitting, and we will also study validation. Now, quick summary. So regularization. You're the learner, you have your hypothesis set, and you're fitting the data. You're getting lower and lower in sample error. But at some point, overfitting kicks in, and your fitting of the data giving you lower and lower in sample error is resulting in higher and higher out of sample error. Okay, so it's time to apply the brakes on the fitting. And that's more or less what regularization does. Remember the overfitting scenarios from the last lecture where we applied the fourth order polynomial, and I posed the question, is it possible to use the fourth order polynomial but not suffer from that weird nonsensical fit? Okay, that can sort of be addressed by this technique that we're going to talk about next, which is regularization. Can we apply the brakes? So then we can get the benefit of a high order polynomial transform, get the benefit of a complex hypothesis set, but be able to apply the brakes to prevent overfitting. That's regularization. Okay. And validation is similar in the sense that it's one of the tools that we have for combating overfitting. Okay, but it does it in a different way. So you're fitting the data, and you're in some kind of a bliss that everything is looking better and better and better and better. But validation comes and gives you a reality check by giving you a peek at the out of sample error. Okay, and says, buddy, you might think that you're getting better and better in sample error, but your out of sample error is getting worse and worse. You are starting to overfit. You better backtrack. Okay, so regularization and validation are next. But I want to just give you I want to whet your appetite and show you some of the power of these tools that we're about to develop. And, things might get a little mathematical, but this is to say, stay tuned, pay attention, because noise is everywhere. Overfitting is a disease that you cannot avoid, so you had better build yourself a cure for it. Okay, so you need to understand regularization because noise is always there. You need to understand validation, a very powerful technique, one of which is to sort of combat overfitting. Okay, so here's the data that the learning problem and the data that, started this discussion of showing you this sort of classic example of overfitting. Okay, and then this applying the breaks tool, this regularization tool, I'm going to show you what happens if we apply a teeny weeny, insy bitsy, small amount of regularization. Wow! Look at that. Tiny amount of regularization takes nonsense to nearly a perfect fit. Okay, nearly a perfect fit to the target function. And that's just a little bit of regularization, just to show you how worth it is to study this tool, regularization. Next, checking out.